Other question from the audience? Okay, now let's move on to the third team. So, Tsinghua University.
Okay, thank you, Professor Chen. Let me share my screen. Okay, can you see now?
Yes.
Okay, thank you. I'm Bong Su from Department of Electrical Engineering in Tsinghua University, and I'm going to give a brief introduction to our model. I've made a simple PowerPoint, not as good as the last two groups, but I will try
it's
my
okay.
best to put it clear. Okay.
Yeah, we're not doing a presentation competition, so don't worry.
Okay. Firstly, I will quickly finish the data section. Okay. As we all know, the MagNet provides us with many different waveforms, which contain many complex harmonic components. So there is a high demand for the feature extraction ability of the model. Okay, and at the beginning, actually, we had a direct plan to try the MLP model. And we did a lot of feature engineering on the given sequence data as the flux density waveform. In terms of time domain features, we selected a lot of direct parameters, such as amplitude, peak-to-peak value, and variance and effective values. And also we do some mathematical process, and we selected the kurtosis and skewness of the data. And in terms of the frequency domain features, we performed FFT on the given data and selected the frequency and amplitude of the second and third harmonic as features. And also to better characterize the relationship between the features, we also use the polynomial features of degree 3, which actually improve the cubic power of the former mentioned features into the model. Then we build an MLP model with 3 layers, and the number of neurons in each layer is 210 and 150 and 30. But actually, we then find out this model did not perform very well in the given testing dataset. And we also find out that it's not very robust for different materials and the excitation waveforms. So it's not very good for transfer learning method. And when facing like complex excitation waveform, it perform not very well. So we then give it up. So we tried another model that is sequence data structure. So actually, we are inspired by Dr. Li and the transformer model, which is very important in NLP field. So we propose the Shuan model. It's actually a combination of LSTM model and the encoder part in transformer, like the left half of the transformer. Okay. Let me briefly introduce our model. So firstly, the input waveform is actually the flux density waveform of then through a linear layer. The data dimension is expanded from a single scalar to a 64-dimensional vector. Then it enters the encoder layer, like the rest half. Okay, as encoder for feature extraction. This mainly utilizes the attention mechanism contained in the encoder layer to extract the overall information of the waveform. So in fact, we believe that through the encoder layer, the model can extract the information within the waveform. Okay, after passing through the encoder layer, each vector contains the whole information about the entire waveform, actually. Then afterwards, the data is subject to a feature compression through the LSTM layer. And then the frequency and temperature are added to the data, and a relatively small MLP layer is applied for the loss prediction. And we also do a simple transfer learning for test dataset. That is, we first use the N87 dataset to train the model in a rather big learning rate, and then fine-tune the model parameters with a small learning rate in the testing materials. And that can better improve the model performance. And then we also adjust our learning rate in the training process, following the formula here. Okay, and we also use the ADAM optimizer to optimize our model parameters. So in brief, I think our model is actually just add an encoder to the LSTM model. to better extract the feature from the waveform. Okay, and I think that's our the whole content of our presentation. Okay.
Very good. Thank you, Bowen. You are an undergrad, right? This is the undergrad team.
Yes. Yes.
Right. So do you guys learn about machine learning from a course, or like just by yourself, or you have to pick up everything yourself?
I think apart from the course, I think there is a course in our school for us to know something about the machine learning and deep learning, but not very strict into it. Just some application.
Got it. Okay. So when you are selecting the encoding architecture, what was your thought behind it? Like you mentioned, you are expanding the feature from like one dimension to many dimensions. What were the thoughts behind your decision?
Okay, it's actually from my perspective, I think a single scalar of the B waveform, like just a point, it cannot hold that much information about the whole waveform. So actually, we do expansion from one scalar to 64-dimensional vector.
So what does the new information, or what's the new feature that you think this approach may add to? So you are basically adding sign information based on what I was reading. You have your B, and then you're expanding this to many signs.
Yes.
What are the possible benefits this step is creating?
Maybe I think it's actually help the model to learn the dependency of each point in the waveform. Like if I just put a single scalar in it, it may be just do a rather simple mathematical equation, but if I do the attention mechanism, maybe it can learn the information within the waveform. Yeah. Yes.
Okay. Yeah. So we tried. We mentioned yesterday. We tried like wavelet transformation, which is sort of similar in some way. You are basically mapping your arbitrary wave to many frequencies or many base waves, and then process that information. But what we find is that for a simple task that we're doing here for MagNet challenge, that step is probably overkilling and usually leads to very large model but not doing much. But if you are targeting a more like transient behavior or complicated memory effects, those methods could be very useful. So yeah, good try, I guess. But I guess it's not the best for this simple competition that we're aiming here.
Okay, thank you.
Great. Thanks. Any question for audience? Haran and Shukai?
No, not really. So the output of your encoder will be what we call the hidden state, or the encoded information, right? And then you passing to a fixed-point neural network, and then you pass this hidden state into this LSTM.
Yes.
I see.
Then and then select the last hidden state of the LSTM as the output of the LSTM layer.
Okay. So you kind of like processing the sequencing by two modules, like both the okay. Got it. Interesting.
Yeah, and that's also maybe some redundant computing is happening because you're processing a sequence twice. So,
yes.
Yeah, but there's argument that, especially from the large language model community, they say, well, just throw huge parameters. When we are designing the competition rules, we were arguing within ourselves, like whether we should put model size as a goal. But ultimately, we decided to do so because we think for the particular problem we're solving, it doesn't make sense to have a huge model
that's true.
For the which is different from the large language model community. But anyway, thanks. And keep doing what you're doing as undergrad teams. Very impressive. Yeah, thanks.
Okay, thank you.
Then the next is National Taiwan University of Technology.